Hello, everybody. I'm trying a little bit something new here. I'm trying to use a different bit of software. We'll see how it goes. So what I want to talk about today is a little bit more about taking the limit of a Riemann sum. The Riemann sum is this construction we have here. This limit, the sum of f of x sub I star delta x. And we've been seeing these as this idea of approximating rectangles. These are often referred to as Riemann sums. So I did another video where I saw how to compute this thing called the definite integral, which is made up of the limit of these sums by figuring out the geometry of the situation and recognizing that these sums represent an area. And so if we can figure out the shape, and it's a shape we already know how to find the area of, we don't have to go through taking the limit. However, sometimes we have to take the limit. And I won't do much of this. In fact, this is the only one I'm going to do in the video. And while these things are interesting and valuable, both in terms of concept, and they're good algebra practice, and they're good at getting used to the notations, and these kinds of notations are going to be showing up not just in calculus classes. Summation notation is a notation that's prevalent all over science. Limits show up everywhere, all kinds of stuff. So there's no harm in doing a lot of these, but it won't be the focus of these videos. We're eventually going to find out how to sidestep these limits, right? I think I said in the beginning that you can think of the story of taking integrals very similar to the story of taking derivatives, where you learn the definition, which involves a limit, but in practice you usually compute them with some other method, something that's less time consuming. Okay, so let's do some of this, but we need a few rules. We need a few rules for dealing with these summations. So we've seen a few of them before. I'm going to write these out again. We've seen that the sum, let's go a little thinner. The sum as I equals 1 to n of a constant c is just c times n. We've seen that the sum as I equals 1 to n, this still seems a little thick. Let's try a little smaller. I equals 1 to n of c, a constant, times some set of terms is the same as adding up, right? So I showed this in a previous video. The idea is just here we're multiplying each term by a constant. The right-hand side is just like factoring it out. This first one is just adding up the number c n times. That's the same as n times c. And one other we had was about, this is just properties of addition, that if you're adding or subtracting a bunch of terms, you can rearrange the order, right? I will put a little disclaimer on this. You are going to, many of you will end up learning about in later courses, and I've done some videos on these infinite series where you're adding up infinite numbers of things. Then the idea of rearranging things becomes much more complicated. But we're not doing infinite series. We're not adding up an infinite set of things, right? We're stopping at some number n. So even if that number is huge, it's always some number. We can add, rearrange addition as we please. So those are three properties we have already. I want to add a few more properties. So I'm going to write three more properties down, and I will prove one of them. And the other two I will leave. They can be proved in similar ways, though a bit more complicated. I'm gonna prove the easy one, but we're going to take them as algebraic facts. So suppose I add the sum from I equals 1 to n of I. What does this mean? I'm adding when I equals 1, then the term is 1. When I equals 2, the term is 2. When I equals 3, the term is 3. So you're adding up 1 plus 2 plus 3 plus 4. Well, it turns out if you do that up to the number n, that you can figure out that sum by simply multiplying n times n plus 1 and dividing by 2. And what if instead of adding up 1 plus 2 plus 3 plus 4, you added up 1 squared plus 2 squared plus 3 squared plus 4 squared and on up to n squared? Well, this one's a little more complicated, but still not terrible. We get this. And there's one more. What if we add up the first n cubes? It turns out you can figure that out by doing n times n plus 1, dividing it by 2, and then squaring it. Okay? So the first three I've shown in other videos. Let's look at this one here, this first one, and see how we can show that. So just to make notation easier, right? So first, let's just write this out. 1 equals n. This is just 1 plus 2 plus 3, dot, 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 up to n. I'm just going to give this a simpler name than this big summation. Whatever this adds up to, let's call it s. And in fact, let me show a couple more terms. Before we get to n, we'll get to n minus 1. And then we'll get to n. So just one more term, right? So that's just the one before the end. All right. I'm going to write the same set of numbers, but backwards. Right? So I'm still adding up all the numbers 1 through n, but I can add them up in the reverse order. There's nothing wrong with doing that. Well, let's add these two equations together. If I take s plus s, and remember what s is just whatever number this adds up to. S plus s gives me 2s. 1 plus n, I'm going to write as n plus 1. N minus 1 plus 2, right? I'm just adding straight down, gives me n plus 1. Right? If I added 3, the next term after n minus 1 would be n minus 2 plus 3, gives me another n plus 1. Right? And this pattern will continue. And then at the end, I have 2 plus n minus 1 gives me an n plus 1. And then I have 1 plus n gives me n plus 1. Right? Well, how many of these do I have? Well, I got one when I added up these two. I got one when I added up these two. I got one of them, right? The next term's not there, and on and on and on. So I get one from here and one from here. So I could just count. I have one of them, two of them, three of them. There's a total of n of them. In other words, n plus 1 plus n plus 1 plus n plus 1. If you have n of those, you have n times n plus 1. Well, now we just divide both sides by 2. We get s equals n over n plus 1 divided by 2. And s was, what's the thing you get when you add up the first n integers? Okay, let's test it really quick. For instance, if I did the first 3 integers, if n equals 3, then I get 1 plus 2 plus 3 gives me 6. On the other hand, n times n plus 1 over 2 is going to be 3 times 3 plus 1 over 2. You can compute that and see that you get 6, right? Test it for a couple more for yourself. See that it continues to work out. It does. And this is a nice formula we have. These other ones are more complicated, but it's a similar idea. You can do some complicated algebra, do some manipulations, and you can show that these sums are equivalent to these formula. All right, so why did we do that? Well, let's compute one of these integrals. Okay, so let's compute these definite integrals, I should say. I want to compute the integral from -1 to 5 of 1 plus 3x dx. Okay. Now, first, my definition. The limit as n goes to infinity. Let's put parentheses in, make it prettier. I equals 1 to n f of x sub I star delta x. Okay. So let's remember what all of these pieces are. I'm just going to go through and figure out what each of these pieces are. Delta x, remember, is b minus a over n. b is 5, a is -1, so I have 5 minus -1 over n. gives me 6 over n. Okay, there's my delta x. X sub I star. Now remember what x sub I star is. X sub I star is any point when we divide up our interval, right? If any point between x sub I minus 1 and x sub I, if I pick any point in here, I call it a sample point in that interval, including the endpoints, then I can use that as the x sub I star. I'm going to stick with right endpoints. That's the one we've been using. That's the one I like the most. It's just easiest to formulate. Remember what our formula for this is. We take a, in this case it's -1, plus I times delta x. All right. Well, in this case, that's -1 plus I times 6 over n, so I'll get 6i over n. Okay? So I sub 1 is -1 plus 6 over n. I sub 2 is -1 plus 6 times 2 over n, and on and on and on. Okay, so depending on how many intervals, how many times we chop this thing up, we'll get a different number of these intervals. Okay, let's keep going. Sorry, I thought I saw an error message. It was not referring to this recording. All right, so where are we? Oh, we've got x sub I. Let's compute f of x sub I, right? See what I'm doing is I'm just picking apart these pieces. I needed delta x. I wrote down an expression for delta x. I needed x sub I. I wrote down an expression for that. Now I'm going to write down an expression for f of x sub I. So f of x sub I is going to be, f is this formula in here, 1 plus 3x. So I'm going to take 1 plus 3, and in place of x, I'm putting x sub I, which is -1 plus 6i over n. Okay? That's a pretty ugly way to write that thing down. You can do a little bit of algebra and get, works out to be -2, 1 minus 9i over n. I'll leave that algebra up to you. It's just expanding the 3, combining things, and factoring something out. So that seems pretty doable. Then, now I'm going to put these things together. I'm going to put f of x sub I and delta x together. F of x sub I, delta x, is just this thing times delta x, which is 6 over n. Let's write that a little bit nicer. -12 over n, 1 minus 9i. Oops, let's give me a little more space here. Over n. Okay, I think that's a good way to write this out. Let's keep going down. Well, let's move to the side here. Okay, so now let's continue. We've got all the pieces we need. We can write this thing out now. So remember what we're doing. Let's kind of regroup. I'm taking this integral from -1 to 5 of 1 plus 3x dx. And I know this is equal to the limit as n goes to infinity, the sum I equals 1 to n of f of x sub I star delta x. But now I've got an expression for this thing in the limit. So let's go ahead and put that in. The limit as n goes to infinity, I equals 1 to n. And I'm just putting in this thing we worked out on the left. -12 over n, 1 minus 9i over n. Okay. Now, I'm just going to use now a bunch of the rules that I had listed up above here. Okay, I'm just going to use a bunch of those rules. So for instance, this 12 over n, this is a constant, right? We're only dealing with the summation. We're doing all the limit stuff at the end. So right now I'm only working within the parentheses. So when I think about the limit, then n's changing. But right now within the parentheses, before I've taken the limit, I've got this sum of the numbers from 1 up to n, where n is some numbers. So this -12 over n is a constant. So I can, in fact, let's No, there's not enough space. I don't know how to, oh, yes, there is. Actually, I can move this screen around. I'm learning. Here we go, folks. In fact, let's do this. Let's just work on this part of this, ignoring the limit for now, and manipulate this expression until it's something we can take a limit of, right? We don't know how to take a limit of as this is written, because while on the one hand, as n gets bigger, negative 12 over n gets smaller, 9i over n gets smaller, those two things go to 0. But at the same time, we're adding up more and more things. So each individual term gets smaller, but we're adding up more things. So for instance, if I started adding up 1 plus 1, I get 2. I could add up more things, but make them smaller, adding up 1/2 plus 1/2 plus 1/2, and I get 3/2, right? And so it's not clear which of those two things is winning. So I don't really know how to take this limit as written. But using the properties of summations, for instance, I can take this constant out front. Right? That was one of our properties. Then I can split up this. I'm adding two terms together, right? We had this property that said if we summed up something like this, we could split this into two different sums. Well, that's what we have. I have 1 is my AIs, 9i over n is my BIs, so I can split this into 1 minus the sum I equals 1 to n of 9i over n. Okay. Well, what happens if I add up the number 1, this first summation, n times? I just get n, right? 1 plus 1 plus 1 plus 1, n times, I get n. In this second summation, 9 over n is also a constant. Just like 12 over n was a constant that we pulled out before. And I've got I. All right, here we go. Now I had that, we developed that property that if I sum up the first I terms, right, 1 plus 2 plus 3 plus 4 and so forth, I get n times n plus 1 over 2. So now I can replace, I've got 9 over n here, I can replace this last summation with n times n plus 1 over 2. Okay. And now I'm just doing some algebra. Okay, I'm going to start by multiplying this negative 12 over n into these parentheses. So negative 12 over n times n gives me negative 12. Negative 12 over n. So this n in the denominator under 12 can cancel with the n in the numerator here. I'll have 12 times 9 divided by 2 gives me 54. There's a negative and a negative makes it positive. What's left is I have n plus 1 over n. Okay, so let's look what happened. This n, the way I did it was this n canceled with this n. I could have canceled the other one, it doesn't really matter. And then negative 12 times negative 9 divided by 2 gave me the positive 54. And so what was left over is an n and an n plus 1. Okay, so this whole summation, this whole complicated summation we have works out to be this expression. And so now I can put that back into this limit formula. So I'm replacing this, right? I did all this work over here to show that this summation is equivalent to this thing right here. Right? So now I have negative 12 plus 54 over n plus 1 over n. And this is something I know how to take the limit of. I have my limit laws. The limit as n goes to infinity of negative 12. Remember, the limits can distribute over addition, so I can take the limit of negative 12 first. Negative 12 doesn't change as n changes, so the limit of negative 12 is just negative 12. The constant can slide in front of the limit, and I take the limit as n goes to infinity of n plus 1 over n. There's a few ways to take this limit. You might remember a rule that if you have a rational function that is a function that is the quotient of two polynomials, if their degrees are the same, which is what we have here, these are both linear polynomials, then the limit is going to be the ratio of their coefficients. In other words, 1 over 1, this limit is 1. I always think of it intuitively when we have something like n plus 1 over n. If I'm making n larger and larger, that will look like 1001 over 1000. That's barely bigger than 1. And then 1,000,001 over 1,000,000,000 is only off from 1 by an extra 1/100000th, right? It's 1 plus 1 over 1,000,000,000. And if I have 1,000,000,001 over 1,000,000,000,000, that's 1 plus 1 over 1,000,000,000,000, right? There's this little extra bit on top, but it barely matters as the numbers get big. So this thing goes to 1. I get -12 plus 54, which gives me 42, right? And so what we're saying here, the definite integral from -1 to 5 of 1 plus 3x dx, oops, I forgot my 1 here, is 42. In other words, there's an area between this graph, 1 plus 3x and 1 plus 3x, between this graph and the x-axis, and the area between those two is 42, okay? Now, that statement's mostly accurate. Let's see, there's one little thing we have to remember here. So let's go ahead and look at a graph, and let's just remember the result we had was 42. So give me a second. Let's share our graph. That's not it. There it is. Okay, I think you were seeing it before I was. So here's a picture of 1 plus 3x, right? It's a slope of 3. It might not look steep enough, but the scales aren't even here. I tried to make a nice picture that we can see everything. One little piece of this that we often forget to call out is the fact that we say it's the area, but when we think of areas, we think of areas as positive. But here, we sometimes say something like the signed area. Areas can be negative. Looking at this graph from -1 to 3, right, here's -1, or to 5, excuse me. Some of the area is negative. So there's two different triangles here. This one below the x-axis will count as negative area. The one above the x-axis will count as positive area. Let's see that our result is good because these are triangles, and I can find the area of these triangles pretty easily. So this triangle here, the one that's below the x-axis, let's compute its area. Remember, we just need 1/2 base times height. Well, the height, so let's just write this. I'll just call this triangle 1. Is going to be 1/2. Let's see, the base, so I'll call the distance along the x-axis here. It goes from -1/3 to -1, so that's a distance of 2/3. Its height is going down here, but it goes from -1, 0 to -1, -2, so that's a height of 2. So A1 as an area, cancel these, and I get is 2/3. Okay, so we're going from -1/3 to 1. Yeah, that's what we've got. 1/2 times 2, we've got our 2/3. Okay, let's look at the other triangle. So I'll just draw that one over here. Its height goes from 5, 0 to 5, 16. So the height is 16. Its base, well, 0 to 5 gives me 5, but I have an extra 1/3 because it goes down to -1/3. So 15, 5 and 1/3 will give me 16/3. And so its area, let's call this triangle 2, A2 is going to be 1/2 16/3 times 16. Okay, so let's see what this works out to be. We can cancel one of these to get 8. We get A2 is equal to, what is that? 8 times 16 is 80 plus 48 is 128/3. Okay, now here's the big idea for our integral, -1 to 5, 1 plus 3x dx. This is the signed area. Again, what I mean is areas below the x-axis are negative, areas above are positive. So this is going to be the positive area, the thing I called A2, minus the negative area. And that's 128 thirds minus 2 thirds, which is 126 thirds, which is equal to 42, which is exactly the result we got just a few moments ago. Okay, a couple of things. Obviously, it probably would have been easier to find this area using triangles, and you're always welcome to do this. I did this as a demonstration because we're adding all this complicated notation and machinery, and sometimes it feels like we're just sort of making things up to complicate your life. This process works, okay? And this one I chose because I wanted to be able to compare it to the area by using shapes we know, in this case triangles, but this process works when it's not shapes we know, when it's something like f of x, right, equals x times e to the x, and we get some kind of, well, that's not what it looks like, but anyways, we get some kind of curve that we don't have a simple formula for, okay? So that's when this, although long process, becomes crucial because we don't have any other options. Another thing, I won't do any more videos, at least not right now, showing how to add up those sums. I want you to have experience doing that, but it's not going to be a focus, right? We're about to get to how we generally compute these without having to use this. I do want to you know, really hammer home though, every time we use our shortcuts, it's still the process, you know, underneath it all is still well understood to be these approximating rectangles. Just like when you take derivatives and you say, oh, the derivative of x squared, I used the power rule, it's 2x. What we really mean is there's this quotient, difference quotient, we take a limit as h goes to 0, and it turns out we can compute that limit easily by the power rule, but we still have this idea of these secant lines where we're pulling the points closer and closer together, getting this instantaneous rate of change. So the intuition behind it is still very important. I guess that's it. I liked the new software I was using, though I apologize, I think my work was a little bit sloppy in it. I'm getting used to how it navigates, but that will get better. I hope it gets better. Thanks, everybody. I will see you the next time.